Alright, tonight's video is hopefully going to be pretty short and to the point. When dealing with the concepts of projectile motion, so tomorrow we're just dealing with concepts, not getting into calculations yet, there are two key points that you really need to get stuck in your head. First, horizontal and vertical motion are completely independent and are calculated independently. So if we have something that's traveling at an angle, a little bit up and a little bit over, we would calculate its travel up and its travel over completely independently. So x and y motion, horizontal and vertical motion, are independent of one another. They don't influence each other and are always calculated separately. Second, on Earth and in the absence of air resistance, all objects fall with the same acceleration. So that part of this statement should just be a review of free fall. And would take the same amount of time to hit the ground if dropped from the same height. So no matter what else is going on with the objects, if they are dropped from the same height, they will hit the ground at the same time. That's what we're going to talk about tonight, and hopefully you'll have a good conceptual understanding, and tomorrow we'll work on the math. Sorry, not tomorrow in class, but tomorrow night we'll work on the math. Alright, so a couple things to review. If you have a constant velocity, your motion will always be in a straight line. And that's by definition. Velocity is same speed and direction. So to have a constant velocity, you can't change your speed and you can't change your direction. It's worth reiterating. Velocity, speed, and direction. If either one of those two things changes, your velocity has changed. So you could keep the same speed, but turn left all of a sudden. And if you do that, your velocity has changed. Speed and direction have to stay the same to have constant velocity, hence the turtle. He has constant velocity and is moving in a straight line. That straight line is diagonal, but he's moving in a straight line. And then to get ready for what we're talking about next, notice down here, we would resolve this turtle's motion into horizontal and vertical components that we then deal with completely separately. All right, moving on. Next up, motion in the x and y direction should be solved separately. To do that, which is what I talked about in the last two slides, there are actually two sets of equations. But if you look at them, you'll notice they're the same. So let's read through. First, the first column where it says position as a function of time. For x, the equation is x equals x naught plus v naught t. And then that's v naught in the x direction, so that's why it says v naught x. So let me start over. X equals x naught plus v naught in the x direction times t plus 1/2 acceleration in the x direction times t squared. And then the analog of that equation in the y, or some, think of the word analog as like synonym, or something similar to. So the analog of the position as a function of time equation in y is y final equals y naught plus v naught in the y direction times t plus 1/2 acceleration in the y direction times t squared. So notice they're the same. You just calculate x and y completely separately. And the same will hold over here. Notice those equations for velocity as a function of time are the same. You just calculate y and x separately, and then velocity is a function of position. You calculate y and x separately. Same equations, just one set is for x and one set is for y. And the reason we have two sets is because you need to remember x and y should be solved separately. So notice I'm saying that a lot. That really needs to be drilled into your head. X and y are always dealt with separately. You can think of the whole world as x's and y's and go on from there. And they're all separate. So we have those basic equations, and here are some assumptions that we're going to make. And these assumptions will actually make more sense to you later in the year. So assumptions. We're going to ignore air resistance. Not going to deal with that. The value for gravity on Earth, I've been kind of fibbing so far, does change. So the higher up you are, the lower the value of acceleration due to gravity. And, let's see, we did a lab in CP, I don't know if we do it in AP, where we actually find what the acceleration of gravity is in my classroom. But for the sake of simplicity, we're going to assume that acceleration due to gravity is 9.81 meters per second squared, and that messed up on the computer, that should be squared, and downward. So that's our assumption. Anything that happens on Earth, we're going to use that value of g, 9.81 meters per second squared, downward. You can use, for simplicity, g is about 10 meters per second squared. However, if you use that in a calculation, you have to tell me that. So in your givens, you would actually write g is about 10 meters per second squared, and then it's fair to use it throughout. You just have to show that that's what you're using for g. We will also ignore Earth's rotation. Earth's rotation actually does influence some of the problems we're going to deal with in this unit, but we're not going to deal with that right now. You'll get little hints of it throughout the year. That's a really advanced concept, though, Earth's rotation. Next up, if y-axis points upward, acceleration in x direction is 0, and acceleration in y direction is negative 9.81 meters per second squared. So if we declare a reference frame, sorry, I've been calling those coordinate systems. I should keep doing that. If we declare a coordinate system, and we call y, positive y up, then acceleration due to gravity must be negative 9.81 meters per second squared. There will be lots of times when it's convenient to make downward the positive y, which some of you actually read about in one of the previous textbook chapters. Don't worry, that'll become more familiar as we actually get into the math in the next couple days. This we talked about on free fall day. Acceleration is independent of velocity. So if I drop the ball straight down, its acceleration is negative 9.81 meters per second squared. If I throw the ball at an angle, its acceleration is negative 9.1 meters per second squared in y, downward. Okay, so notice, even if our ball did have an x acceleration, even if someone was pushing it straight along x, its acceleration downward would be negative 9.81 meters per second squared. No matter what's going on in x, your y acceleration is still gravity. Now, if you were to hold the ball or push the ball up or down, that would change. You're influencing what happens in y. But if you're just changing things in x, your acceleration in y is always little g, 9.81 meters per second squared, downward. So, acceleration is independent of the direction of velocity. No matter which way I throw the ball here, any of these ways, its acceleration would still be negative 9.81 meters per second squared. So, what we can do is actually reduce the equations down to some simpler forms. Let me show you what I mean. So, over on the side, pay attention to what I'm writing instead of what's on the screen, or what's typed for a second. We have some equations like x equals x naught plus v naught t plus 1/2, I'm going to run out of room, at squared, v equals v naught plus a t, and then, v squared equals v naught squared minus 2a delta x. And we have the same in y. Because we know that x for a projectile, something that's thrown and then not pushed, because we know it won't have any acceleration, we can eliminate the acceleration terms, because they'll be 0, from each of these equations. So I can take out the acceleration here, and I can take out the acceleration here, and I can take out the acceleration here. Which then means these equations reduce, for the x part, down to these. So notice, all that's happened is this first equation on the page, x equals x naught plus v naught xt, is the equation I had up here, just with acceleration removed, because acceleration in x is 0. Same thing here, acceleration is x and 0, so we've just taken out that term, and same thing here. So these equations on the screen you don't actually have to memorize, because you already know, hopefully, these over here, and if you know acceleration in x is 0, you can get these other equations out of that. And then y does have an acceleration, but we know it. The acceleration in y is negative 9.81 meters per second squared, or g. And so we can write those equations with g already in them when we're dealing with projectile motion. So notice these are just the 3 kinematic equations you already know. rewritten for projectile motion. And you don't have to memorize them, you just have to know how to get to them. You have to know that in y the acceleration is acceleration due to gravity on Earth, and then in x, acceleration is 0. And that's how these come about. And that's it. If you know all those things, you're good. Like I said in the post on the website, you should look back over section 3.3 now that you've watched the video. A lot of things there are going to make sense. In fact, reading it all the way through after watching this video is probably going to make a lot of sense to you, and I highly recommend that. This video also should have clarified some of the things I asked you to do during the reading, so you might want to go back and take a look at those. Also, make sure you've answered the post-reading question, and there is extra practice, I do believe, on projectile motion. Make sure you do that if needed. And that's all. Have a good night.